Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Maybe you've had one of those days where your mind won't quiet down, or perhaps you're the kind of person who finds peace in the gentle wisdom of the natural world rather than counting sheep. Either way, tonight's journey is crafted just for you. We'll wander gently through forests of facts, from the way trees communicate in whispers we're only beginning to understand, to the remarkable ways they've learned to survive and thrive across millennia. You'll discover how some trees can live for thousands of years, how they create their own weather, and the surprising connections they share with every living thing around them. If these peaceful explorations help you unwind or give you a moment of calm in your day, consider liking and subscribing to the channel. It helps other weary souls find their way here too, one restful night at a time. Now, let yourself get completely comfortable, take a deep breath, and let's begin this slow and soothing journey through the most relaxing facts about trees. The oldest living trees have been growing since before the pyramids were built. High in the mountains of California, twisted and weathered by wind and time, bristle-cone pine trees continue their slow dance with the seasons. Some of these ancient beings have been alive for over 4,000 years. They were already centuries old when the Great Pyramid of Giza was constructed. They've watched civilizations rise and fall, ice ages come and go, and countless generations of smaller plants and animals live their entire lives in their shadows. These trees don't grow fast or tall. Instead, they've mastered the art of persistence. Their wood is so dense and resinous that it resists decay, insects, and disease. In the harsh mountain environment where they thrive, they grow perhaps 1 millimeter wider each year. Each ring in their trunk is a year's worth of patience, a single breath in a life measured not in decades, but in millennia. When you look at a bristlecone pine, you're looking at a living library of climate history, a being that has felt the touch of more sunrises and sunsets than any human could imagine. They stand as quiet monuments to endurance, teaching us that sometimes the secret to longevity isn't speed or size, but simply the gentle art of not giving up. Trees can live for months without their leaves and still survive perfectly well. Every autumn, deciduous trees perform what might seem like an act of surrender. They release their leaves, letting go of the very organs they use to capture sunlight and create food. Yet this apparent sacrifice is actually one of nature's most elegant survival strategies. As winter approaches and sunlight becomes scarce, maintaining leaves would cost more energy than they could provide. So trees pull all the valuable nutrients back into their trunks and branches, storing them like a savings account for spring. The chlorophyll that kept the leaves green breaks down, revealing the yellows, oranges, and reds that were there all along, hidden beneath the surface. Once the leaves fall, trees enter a state similar to hibernation. Their metabolism slows dramatically. They stop growing, reduce their water intake, and settle into patient wait-in. Beneath the bark, life continues at a whisper's pace. The roots remain active, slowly gathering moisture and minerals. The trunk stands strong, weathering storms and cold while protecting the tree's essential core. This leafless time isn't emptiness, it's rest. It's the tree's way of conserving energy, of preparing for the explosive growth that will come with spring's return. In their bare branches against winter skies, trees teach us that sometimes the most productive thing we can do is simply be still. Some trees can warn their neighbors about danger through underground networks. Beneath the forest floor, invisible to our eyes, lies one of nature's most sophisticated communication systems. Tree roots don't grow alone in the soil. They intertwine with delicate fungal threads called mycorrhizae, creating a vast underground internet that scientists have begun calling the Wood Wide Web. Through this network, trees can send chemical messages to one another. When a tree is attacked by insects, it releases compounds through its roots that travel through the fungal connections to nearby trees. These chemical signals act like an early warning system, allowing neighboring trees to begin producing defensive compounds before the threat reaches them. Mother trees, the largest and oldest in the forest, act like hubs in this network. They can recognize their own offspring and send them more resources through the underground connections. If a young tree is struggling in deep shade, its parent can share sugars and nutrients, helping it survive until it's strong enough to compete on its own. This hidden conversation never stops. Trees share resources during times of plenty and support each other during drought or disease. They've been practicing community care for millions of years, creating forests that function not as collections of individuals competing for resources, but as interconnected communities where the health of one affects the well-being of all. The tallest trees on Earth create their own weather systems. In the coastal forests of Northern California, coast redwoods rise like living skyscrapers, some reaching heights of over 300 feet. These gentle giants don't just live in their environment. They actively create and modify it, generating their own weather in a process both beautiful and essential to their survival. As morning fog rolls in from the Pacific Ocean, it encounters the towering canopy of the redwood forest. The massive trees act like giant combs, capturing moisture from the fog on their needle-covered branches. This captured water condenses and drips down to the forest floor, providing up to 40% of the tree's water needs during the dry summer months. But the redwoods don't just harvest fog, they help create it too. Through transpiration, they release millions of gallons of water vapor into the air each day. This moisture rises, cools, and forms the very fog that will return to nourish them. It's a perfect cycle, a conversation between the forest and the sky that has continued for millions of years. The climate beneath these towering trees remains remarkably stable. The canopy creates a natural air conditioning system, keeping temperatures cool and humidity high. Even on the hottest summer days, walking into a redwood grove feels like stepping into a natural cathedral, where the air is soft and cool, filtered through hundreds of feet of living branches. Trees can count days and remember seasons with remarkable accuracy. Trees don't have brains or nervous systems, yet they possess a form of memory that would impress any computer scientist. They can track the passage of days, remember the length of seasons, and even anticipate changes in weather patterns based on subtle environmental cues. Each tree maintains an internal calendar based on daylight hours, temperature fluctuations, and seasonal rhythms. They know when winter is truly over, not just because of a few warm days, but because they can measure the gradual lengthening of daylight that signals spring's genuine arrival. This prevents them from budding too early during temporary warm spells that might be followed by killing frosts. Some trees require a specific number of cold days before they'll produce flowers or fruit. Apple trees, for instance, need several hundred hours of temperatures below 45 degrees Fahrenheit during their dormant period. They literally count these cold hours, and only when their internal quota is met will they bloom in spring. This biological memory extends beyond single seasons. Trees can remember droughts, abundant years, and other significant events, encoding these experiences in their growth patterns. A tree that survived a particularly harsh winter might grow more conservatively for several years afterward, investing extra energy in root development rather than height growth. The way trees remember isn't like human memory, but rather a complex biological record-keeping system that helps them make decisions about when to grow, when to reproduce, and when to prepare for challenging conditions ahead. Forest bathing has been scientifically proven to reduce stress and boost immune function. In Japan, the practice of Shinrin-yoku, or forest bathing, has been studied extensively by researchers who wanted to understand why spending time among trees feels so restorative. What they discovered goes far beyond the simple pleasure of being outdoors. When we walk slowly through a forest, breathing deeply and engaging our senses, measurable changes occur in our bodies. Stress hormones like cortisol decrease significantly. Blood pressure drops. Heart rate becomes more variable, a sign of a relaxed nervous system. Even our immune function improves, with increased activity of natural killer cells that help fight infections and disease. These benefits aren't just psychological. Trees release airborne chemicals called phytoncides, natural compounds that protect them from harmful bacteria, fungi, and insects. When we breathe in forest air, we also inhale these beneficial chemicals, which appear to boost our own immune systems. The visual patterns of forests, with their fractal branching structures and organic shapes, seem to have a calming effect on our minds. Unlike the straight lines and harsh angles of urban environments, the gentle curves and natural asymmetry of trees activate the parasympathetic nervous system, promoting rest and healing. Even the sound environment of forests contributes to their healing effect. The soft rustling of leaves, the distant call of birds, and the whisper of wind through branches create what researchers call a natural soundscape that helps mask the harsh noises of modern life and allows our nervous systems to truly relax. Trees have been on Earth for over 350 million years, surviving every mass extinction event. Long before dinosaurs walked the Earth, before flowers bloomed, before grass covered the ground, there were trees. These ancient forests looked different from today's woodlands, dominated by giant ferns and primitive conifers. But they established the template that would allow trees to become one of the most successful life forms our planet has ever known. Trees have witnessed and survived 5 major mass extinction events, including the catastrophic asteroid impact that ended the age of dinosaurs. While 90% of all species perished during the most severe extinction event, trees found ways to endure. Their ability to go dormant, their deep root systems, and their capacity to regrow from stumps and fallen logs gave them resilience that many other life forms lacked through ice ages and warming periods, through volcanic eruptions and meteor impacts, through the rise and fall of countless species. Trees have maintained their quiet presence on Earth. They've adapted to every continent except Antarctica, learned to thrive in deserts and swamps, on mountains and in valleys, always finding ways to capture sunlight and create the oxygen that most other life depends upon. This incredible persistence has allowed trees to become the foundation of most terrestrial ecosystems. They create the conditions that allow countless other species to flourish, providing food, shelter, and the complex three-dimensional habitat that supports everything from soil microbes to flying birds. In their rings, trees carry the history of our planet. In their branches, they hold the promise of its future. They are living links to Earth's deep past and patient guardians of its ongoing story. Human hearts naturally synchronize with the rhythm of rustling leaves. There's something almost magical that happens when we sit quietly beneath a tree on a breezy day. As we listen to the gentle sound of leaves moving in the wind, our breathing tends to slow and deepen. Our heart rate often adjusts to match the natural rhythm of the rustling above us. This synchronization isn't coincidence, but rather an example of how deeply connected we remain to the natural world. The sound frequencies produced by leaves in a light breeze fall within a range that seems to resonate with our own biological rhythms. It's as if trees are playing a lullaby specifically tuned to calm human nervous systems. Different trees create different soundscapes. The large, broad leaves of a maple create a soft, swishing sound, while the needle-covered branches of pines produce a higher, more whispered rustling. Each species offers its own version of natural music, a gentle acoustic environment that can help quiet busy minds and racing thoughts. This rhythmic connection may explain why so many people report feeling more peaceful after spending time under trees. Even if they're not consciously aware of the sounds around them, our bodies seem to remember an ancient partnership with forests, a relationship that developed over millions of years of human evolution in woodland environments. Trees continue growing throughout their entire lives, never truly reaching old age. Unlike animals, which reach maturity and then gradually decline, trees follow a different biological path. As long as they have access to sunlight, water, and nutrients, they can continue growing larger and stronger for centuries or even millennia. This doesn't mean trees don't face challenges as they age. Older trees may grow more slowly, and they can become vulnerable to storms, diseases, or environmental changes. But unlike human cells, which have built-in limits to how many times they can divide, tree cells retain the ability to multiply indefinitely under the right conditions. This means that, in theory, if a tree could avoid accidents, disease, and environmental catastrophes, it could live forever. Some trees seem to be testing this possibility. The ancient bristlecone pines show no signs of aging in the traditional sense. Their oldest specimens are just as capable of producing new growth as trees a fraction of their age. This biological immortality gives trees a fundamentally different relationship with time than most other living things. They don't rush to reproduce before their bodies fail. Instead, they can afford to grow slowly, to wait for perfect conditions, to invest decades or centuries in building the strength and resources needed to thrive in their chosen location. In their patient, persistent growth, trees offer a different model for thinking about life and time. One based not on urgency, but on endurance. Not on speed, but on sustainability. A single tree can be home to thousands of different species throughout its lifetime. If you could shrink down and explore a single mature oak tree, you would discover an entire universe of life. From the tip of its highest branches to the deepest reaches of its root system, one tree can provide habitat for thousands of different creatures, creating a vertical ecosystem that rivals the diversity of entire meadows. In the canopy, countless insects make their homes among the leaves. Caterpillars munch on fresh foliage while spiders weave webs between branches. Birds build nests in the safety of strong limbs, and squirrels hollow out dens in tree cavities. Each layer of the tree offers different conditions, different resources, and different opportunities for life to flourish. The bark itself becomes a miniature landscape. Mosses and lichens carpet its surface, creating soft gardens that hold moisture and provide food for tiny creatures. Beetles burrow through the outer layers, while ants create highways along its ridges and valleys. Even the spaces between bark plates become shelters for overwintering insects and small reptiles. Below ground, the root system supports its own hidden community. Earthworms tunnel through the soil, aerating it and breaking down organic matter. Beneficial bacteria cluster around root tips, helping the tree absorb nutrients. Mycorrhizal fungi form partnerships with the roots, extending the tree's reach into the soil while receiving sugars in return. As the tree ages and parts of it die back, it continues providing for life in new ways. Dead branches become homes for woodpeckers and cavity-nesting birds. Fallen logs slowly decompose, becoming nurseries for new plants and homes for salamanders, insects, and countless microscopic organisms. Even in death, trees give life. Their bodies becoming the foundation for future forests, trees can recognize and prefer their own offspring in the forest community. Deep in the forest, family relationships exist that we're only beginning to understand. Through chemical signals and underground fungal networks, parent trees can identify their own seedlings among the countless young plants scattered across the forest floor. When resources are scarce, mother trees make choices about where to send nutrients and support. Research has shown that they preferentially share resources with their own genetic offspring, sending more carbon, nitrogen, and other essential nutrients to their children than to unrelated seedlings nearby. It's a form of parental care that happens entirely through chemical communication and underground connections. This recognition system appears to work through chemical signatures, unique molecular fingerprints that allow trees to distinguish family members from strangers. Young trees growing near their parents receive not just nutrients, but also important information about local growing conditions, seasonal patterns, and environmental challenges. The bonds between tree families can last for decades. Adult trees may continue supporting their offspring long after the younger trees have grown large enough to survive on their own. These family networks create pockets of genetic similarity within forests, where related trees cluster together and support each other through good times and challenging periods. This discovery has changed how scientists think about forests. rather than seeing them as collections of individual trees competing for resources. We now understand them as complex family communities where cooperation and mutual support are as important as competition. Some trees can change their gender from year to year based on environmental conditions. In the quiet corners of forests around the world, certain trees practice a form of biological flexibility that seems almost magical. These species can switch their gender from one growing season to the next, producing male flowers one year and female flowers the next, or sometimes both types simultaneously. This gender switching isn't random, but represents a sophisticated response to environmental conditions and resource availability. When a tree has abundant energy stores and ideal growing conditions, it might produce female flowers and invest in creating seeds and fruit. During leaner years or stressful conditions, the same tree might switch to producing only male flowers, which require less energy investment. Some trees make these decisions based on their size and maturity. Young trees often begin their reproductive lives as males, producing pollen rather than energy-expensive seeds. As they grow larger and stronger, they may switch to female reproduction, using their increased resources to create the next generation. Environmental factors like rainfall, temperature, and soil nutrients all influence these gender decisions. Trees seem to have an innate understanding of when conditions are right for the enormous investment required to produce seeds and fruits, versus when it's better to contribute to reproduction through pollen production alone. This reproductive flexibility helps ensure that tree populations can continue even when conditions aren't ideal. In challenging years, some individuals focus on pollen production, while others invest in seed creation, spreading the reproductive effort across the community and increasing the chances that some offspring will survive. Trees communicate through airborne chemicals that can travel for miles on the wind above the forest canopy. Invisible messages drift on every breeze. Trees release volatile organic compounds, chemical signals that can carry information across vast distances, creating a communication network that spans entire forests and beyond. When a tree comes under attack from insects or disease, it doesn't suffer in silence. Within minutes, it begins producing chemical alarm signals that drift upward into the air. These molecular messages can travel for miles on wind currents, warning distant trees about the approaching threat and giving them time to boost their own defenses. Different threats trigger different chemical messages. The compounds released during a caterpillar attack are distinct from those produced when a tree faces drought, stress, or fungal infection. Trees receiving these signals can prepare appropriate responses, whether that means producing bitter compounds to deter insects, strengthening their immune systems, or beginning to conserve water. This airborne communication system connects forests across landscapes. A tree under stress in one valley can send warning signals that reach trees on distant hillsides. The chemical messages carry information not just about immediate threats, but also about changing seasonal conditions, weather patterns, and resource availability. Some of these chemical signals can even cross species barriers. While trees communicate most effectively with their own kind, many can interpret basic distress signals from different tree species, creating broad alliance networks that span entire forest ecosystems. The Amazon rainforest produces more than 20% of the world's oxygen, while breathing out enough moisture to influence weather patterns across continents. The vast Amazon basin functions as one enormous lung for our planet, inhaling carbon dioxide and exhaling oxygen on a scale that's difficult to comprehend every day. The billions of trees in this tropical forest produce enough oxygen to supply the breathing needs of millions of people around the world. But the Amazon's influence extends far beyond oxygen production. Through transpiration, the forest releases an estimated 20 billion tons of water vapor into the atmosphere each day. This moisture doesn't just disappear. It becomes part of global weather systems, contributing to rainfall patterns across South America and beyond. The water cycle created by the Amazon is so powerful that it generates its own weather. Moisture evaporated from the forest canopy rises, forms clouds, and falls again as rain, sometimes multiple times as it travels across the basin. This recycling system means that much of the rain falling in the western Amazon originally fell as rain in the eastern Amazon, picked up by trees and released again into the sky. This massive forest also acts as a climate stabilizer for the entire planet. The dark green canopy absorbs enormous amounts of solar energy, preventing it from reflecting back into space and influencing global temperature patterns. The forest's role in storing carbon helps regulate atmospheric composition, while its influence on air currents affects weather patterns as far away as North America and Europe. Scientists have discovered that the health of the Amazon affects rainfall patterns in places as distant as the American Midwest and the European countryside, demonstrating how deeply interconnected our planet's forest systems really are. Trees in cities grow faster but live shorter lives than their forest cousins. Urban trees face a unique set of challenges that create a completely different life experience from their woodland relatives surrounded by concrete and asphalt. With access to supplemental water and fertilizer, city trees often grow remarkably quickly, sometimes reaching maturity in half the time it would take in a natural forest. The abundance of carbon dioxide in urban environments, combined with heat island effects and often generous watering schedules, can create ideal growing conditions for young trees. Street trees may add several inches to their diameter each year, far outpacing the growth rates typical in natural forests where competition for resources is fierce. However, this rapid growth comes at a cost. Urban trees face stresses unknown in natural environments. Air pollution coats their leaves, interfering with photosynthesis. Road salt damages their roots during winter months. Compacted soils make it difficult for root systems to spread and find nutrients. The heat and light reflected from buildings and pavement can create extreme temperature fluctuations that stress the tree's biological systems. These challenging conditions mean that while city trees may grow fast, they typically live much shorter lives than forest trees. An urban maple might live 40 to 60 years, while its forest counterpart could easily survive for over a century. The trade-off between rapid growth and longevity reflects the different survival strategies required in natural versus human-modified environments. Despite these challenges, urban trees provide enormous benefits to city dwellers. They clean the air, provide cooling shade, reduce stormwater runoff, and create pockets of nature in concrete landscapes. Each city tree works harder and faces more stress than forest trees, making their contribution to urban life all the more remarkable. The sound of wind through pine needles has been used as a natural remedy for anxiety for thousands of years, long before modern medicine understood the science behind forest therapy. Human cultures around the world recognized the calming power of pine forests. The distinctive whisper of wind moving through needle-covered branches creates a sound frequency that seems specifically designed to quiet human anxiety and promote peaceful sleep. Pine needles are shaped differently from broad leaves, creating a unique acoustic signature when moved by air. Instead of the rustling or swishing sounds made by deciduous trees, pine needles produce a soft, high-pitched whisper that masks other sounds while creating a consistent, gentle background noise. This natural white noise helps quiet busy minds and can make it easier to fall asleep or enter meditative states. Different species of pine create subtly different sounds. The long needles of white pines create a softer whisper, while the shorter, denser needles of spruce trees produce a slightly more pronounced rustling. Each species offers its own version of natural sound therapy, an acoustic environment that seems to resonate with human nervous systems in particularly soothing ways. Ancient healing traditions from around the world incorporated pine forest environments into their practices. Native American traditions often included time spent among pine trees as part of healing rituals, while traditional Chinese medicine recognized pine forests as beneficial for both physical and mental health. Modern research has begun to explain why these traditional practices were so effective. The combination of phytoncides released by pine trees, the visual patterns of needle-covered branches, and the distinctive acoustic environment they create all contribute to measurable reductions in stress hormones and improvements in mood and sleep quality. Trees can live for decades with their hearts completely hollow, supported only by the living wood just beneath their bark. Some of the most magnificent trees you'll ever encounter are essentially hollow shells, their centers long since rotted away, yet continuing to thrive and grow as if nothing had changed. This remarkable ability reveals one of the most fascinating secrets of tree biology. A tree's heartwood, the dead center portion that gives the trunk its strength and stability, can decay over time due to fungal infections, insect damage, or simply age. Yet the tree continues living because all of its vital functions happen in the thin layer of living tissue just beneath the bark. This layer, called the cambium, is where the tree actually grows, transporting water and nutrients up and down the trunk. As long as this outer living layer remains healthy, a tree can function perfectly well, even with a completely hollow center. The outer shell of living wood is often strong enough to support the tree's weight and withstand storms. Many ancient oaks, chestnuts, and other long-lived species develop hollow centers as they age, creating natural cavities that become homes for countless creatures. These hollow trees often become the most ecologically valuable members of the forest community. Their cavities provide nesting sites for owls, dens for small mammals, and shelter for bats. Some hollow trees can accommodate entire ecosystems within their empty centers, supporting life in ways that solid trees cannot. The ability to survive with a hollow center also helps explain how some trees can live for such extraordinary lengths of time. By shedding their dead heartwood, they reduce their overall weight while maintaining all of their essential life functions, allowing them to continue growing for centuries beyond what might seem possible. Tree roots typically extend 2 to 3 times wider than the tree is tall, creating vast underground territories. When you look at a tree, you're seeing only half of the organism. Below ground, an equally impressive structure spreads outward in all directions, creating a root system that often covers an area 2 to 3 times wider than the tree's height. A 60-foot oak tree may have roots extending more than 150 feet in every direction. These extensive root systems rarely grow straight down into the earth. Instead, most tree roots spread horizontally through the upper layers of soil, typically staying within the top 3 feet, where oxygen, nutrients, and moisture are most abundant. This creates vast underground territories where neighboring trees' root systems interweave in complex patterns. The root tips are where most of the tree's absorption activity occurs. These tiny hair-like structures are constantly growing, dying, and regenerating, creating an ever-changing network that can respond quickly to changes in soil conditions. A single large tree may have millions of root tips actively exploring the soil at any given time. Root systems also serve as the tree's anchor, providing stability against storms and strong winds. The widespread network distributes the tree's weight across a large area and creates multiple points of attachment to the earth. Trees with damaged or restricted root systems become much more vulnerable to being uprooted, which explains why urban trees often fail during storms, when their roots have been constrained by sidewalks and buildings. This hidden underground network also explains why removing one tree from a forest can affect neighboring trees. The interconnected root systems and their associated fungal partners create dependencies that may not become apparent until years after a tree is removed. Some trees drop their leaves all at once in a single day, creating nature's most peaceful snowfall. While most deciduous trees shed their leaves gradually over several weeks, certain species have perfected the art of synchronized leaf drop. On one perfect autumn day, when conditions of temperature, humidity, and wind align just right, an entire tree can release its foliage in what seems like slow motion. The ginkgo tree is perhaps the most famous practitioner of this gentle spectacle. These ancient trees, unchanged for millions of years, hold on to their fan-shaped leaves throughout the fall until one crisp morning when they simply let go. Within hours, the tree stands bare while the ground beneath becomes carpeted in a perfect circle of golden leaves. This synchronized dropping isn't random, but represents a carefully timed biological decision. The tree has been preparing for this moment for weeks, gradually shutting down chlorophyll production and withdrawing nutrients from the leaves. When the final chemical signal is sent, every leaf releases its hold simultaneously, creating one of nature's most serene and meditative displays. Standing beneath a tree during this gentle leaf fall feels almost ceremonial. The leaves drift down like large, soft snowflakes, landing with the barest whisper of sound. The air fills with a golden glow as thousands of leaves catch and scatter the sunlight during their descent. It's a moment that seems to slow time itself, creating a natural meditation on letting go and seasonal change. This sudden transformation from fully leafed to completely bare also demonstrates the tree's remarkable efficiency. Rather than expending energy over weeks to maintain weakening leaves, the tree makes one decisive choice to enter its dormant phase, conserving all its resources for the long winter ahead. Trees can sense the approach of storms hours before weather instruments detect them. Deep in their tissues, trees possess what amounts to a biological barometer system that can detect minute changes in atmospheric pressure, humidity, and electromagnetic fields that precede major weather events. This early warning system allows them to prepare for storms in ways that often help them survive conditions that might otherwise prove destructive. As atmospheric pressure begins to drop in advance of an approaching storm system, trees respond by adjusting their internal water pressure. They may begin closing their stomata, the tiny pores on their leaves, to reduce water loss during the high winds to come. Some trees actually alter the angle of their leaves, positioning them to offer less resistance to anticipated gusts. The electromagnetic changes that accompany storm fronts also appear to trigger responses in trees. Their root systems seem to sense these subtle electrical shifts and may begin anchoring more firmly by expanding root tip growth in the hours before a storm arrives. This preparation can mean the difference between survival and being uprooted when powerful winds finally reach the forest. Trees also respond to the specific humidity patterns that precede different types of storms. Before ice storms, they may begin moving sugars out of their branch tips to prevent cellular damage from freezing. Prior to severe thunderstorms, they often reduce the amount of water in their upper branches, making them more flexible and less likely to break under wind stress. This storm-sensing ability has been observed by foresters and naturalists for centuries, though the mechanisms are only now being understood. Trees that grow in storm-prone areas seem to develop particularly acute sensitivity, becoming living weather stations that can predict dangerous conditions more accurately than many human instruments. Forest floors are covered by a living carpet that recycles nutrients for hundreds of years. Beneath your feet in any mature forest lies one of nature's most sophisticated recycling systems. The forest floor isn't just a collection of dead leaves and fallen branches, but rather a complex, living community that slowly transforms organic matter into the nutrients that feed the entire forest ecosystem. This process begins the moment a leaf falls. Within days, it becomes home to countless microscopic organisms, bacteria, and fungi that begin the slow work of decomposition. Tiny springtails, mites, and other soil creatures join the process, chewing and tunneling through the decaying matter. Each organism plays a specific role in breaking down complex organic compounds into simpler forms that tree roots can absorb. The forest floor operates on multiple timescales simultaneously. Fresh leaves may decompose within a single growing season, while fallen logs can take decades or even centuries to fully break down. This creates layers of decomposition, from the fresh litter on top to the rich, dark humus deep below, each layer supporting different communities of organisms. What makes this system remarkable is its efficiency. Almost nothing is wasted. Every fallen leaf, every dropped twig, every piece of bark becomes part of the nutrient cycle. The forest essentially feeds itself, creating a closed-loop system where the waste of one generation becomes the foundation for the next. This recycling carpet also acts as a giant sponge, absorbing rainfall and releasing it slowly into streams and groundwater. It moderates soil temperature, provides habitat for countless creatures, and creates the rich, organic soil that allows forests to thrive in places where the underlying rock or sand would otherwise support little plant life. Ancient trees carry the memory of past climates in their growth rings, creating libraries of weather history. Every year, as a tree grows, it adds a new ring of wood beneath its bark. These rings aren't just markers of age. They're detailed records of the environmental conditions the tree experienced during each growing season. Wide rings indicate years of abundant rainfall and favorable growing conditions, while narrow rings reveal years of drought, disease, or other stresses. Scientists who study these tree rings, called dendrochronologists, can read the climate history of entire regions by examining the patterns in ancient wood. They've discovered records of major volcanic eruptions, when ash in the atmosphere reduced sunlight and created unusually narrow growth rings across entire continents. They've found evidence of severe droughts that lasted for decades and periods of unusual warmth or cold that affected tree growth patterns. Some of the most valuable climate records come from trees that lived in extreme environments where growth was limited by a single factor, usually temperature or moisture. High-altitude trees that grow near the tree line provide excellent records of temperature changes over centuries. Trees growing in desert margins record the subtle shifts in precipitation that can mean the difference between survival and death. These living libraries extend our understanding of climate far beyond human written records. While we have detailed weather measurements going back only a few centuries, tree ring records can reveal climate patterns spanning thousands of years. Ancient bristlecone pines have provided climate data going back over 4,000 years, showing natural climate variations that occurred long before human influence. By combining tree ring data from many different species and locations, scientists can reconstruct detailed pictures of past climates, helping us understand the natural rhythms of weather and climate change over time scales much longer than human experience. Trees growing on mountainsides lean slightly uphill to counteract gravity throughout their lives. Walk through any steep forest, and you'll notice something subtle but remarkable. Trees growing on slopes don't stand perfectly vertical like their flat-ground cousins. Instead, they lean slightly uphill, their trunks curved in a gentle arc that seems to defy gravity while actually working in harmony with it. This uphill lean isn't accidental, but represents a lifelong process of gravitational response called gravitropism. As a young tree germinates on a slope, gravity pulls its stem downhill, but specialized cells within the tree can sense this gravitational pull and respond by producing growth hormones that cause the uphill side of the stem to grow faster than the downhill side. This differential growth creates a gentle curve that gradually brings the tree's growing tip back toward vertical, even though its base remains anchored on the sloped ground. The process continues throughout the tree's life, creating trunks that curve gracefully uphill in their lower sections, while reaching toward the sky with their upper branches. The curvature isn't just aesthetic, it's essential for the tree's survival. By maintaining an upward growing crown, the tree ensures its leaves can capture maximum sunlight. The curved base also provides better structural support on uneven ground, distributing the tree's weight more effectively across the slope. Different tree species show different degrees of this gravitational response. Fast-growing trees often show more pronounced curves as they rapidly adjust their growth patterns, while slower-growing species may show subtler bends that develop over many decades. Some trees growing on very steep slopes create dramatic curved bases that look almost like natural sculptures carved by invisible forces. The wood formed during this gravitational response process is often denser and stronger than normal wood, creating what foresters call reaction wood. This specialized tissue helps provide the extra strength needed to support a tree growing at an angle to gravity. Some trees can photosynthesize through their bark when their leaves are gone. Most of us think of photosynthesis as something that happens only in leaves, but many trees have developed the ability to capture sunlight and create energy through their bark as well. This adaptation is particularly valuable for trees living in harsh environments or during the months when they've shed their leaves. The bark photosynthesis process works similarly to leaf photosynthesis, but on a much smaller scale. Specialized cells in the outer bark contain chlorophyll and can convert sunlight, carbon dioxide, and water into sugars. While this bark-based energy production can't match the output of a full canopy of leaves, it provides valuable supplemental energy during lean times. This ability is especially important for young trees that don't yet have extensive leaf systems, and for trees recovering from damage. A tree that has lost its leaves to drought, disease, or insect attack can continue producing some energy through its bark while it works to regrow its foliage. This backup energy system can mean the difference between survival and death during stressful periods. Trees in desert environments often rely heavily on bark photosynthesis. Species like the Palo Verde tree have developed green bark that can photosynthesize year-round, allowing them to survive in environments too harsh for traditional leaf-based energy production. These trees may actually produce more energy through their bark than through their small, drought-adapted leaves. The chlorophyll in photosynthetic bark often gives tree trunks and branches a greenish tint, particularly visible in young trees or on newly grown branches. As bark ages and thickens, this photosynthetic capacity usually diminishes, but it remains an important backup system throughout the tree's life. Even common temperate trees like aspens and birches can photosynthesize through their bark, particularly in their younger branches. This helps explain why these trees often maintain their green-tinged bark coloration, and why pruning cuts on young branches heal so quickly. Trees can adjust their wood density based on the mechanical stresses they experience throughout their lives. Every tree is essentially a living engineer, constantly monitoring the forces acting upon it and adjusting its structure accordingly. Trees growing in windy locations develop denser, stronger wood than those in protected areas. Trees that regularly sway develop different internal structures than those that grow in still air. This process, called adaptive growth, allows trees to custom build their own support systems based on their specific environmental challenges. A tree growing on a windy ridgetop will gradually increase the density of its wood fibers, creating a trunk that can withstand stronger forces. The cells in areas of high stress become smaller and more tightly packed, while areas under less mechanical stress may develop larger, less dense cells. The tree's ability to sense and respond to mechanical stress is remarkably sophisticated. When wind causes a tree to bend, specialized cells detect the compression and tension forces acting on different parts of the trunk. These cells then signal for the production of reaction wood, specialized tissue that provides extra strength where it's needed most. Trees also adjust their shape based on the patterns of stress they experience. A tree regularly blown by wind from one direction will develop a stronger root system on the windward side and may grow more branches on the leeward side. To balance its weight distribution, trees growing in snow-heavy areas often develop more flexible branches that can bend under load without breaking. This adaptive growth process continues throughout a tree's life, allowing it to respond to changing conditions. A tree that grows up in a protected forest setting but then becomes exposed due to logging or storm damage can actually strengthen its wood in response to the new wind exposure, though this process takes several years to complete. The wood produced under different stress conditions can vary dramatically in its properties. Woodworkers and craftspeople have long recognized that trees grown in challenging conditions often produce the strongest, most beautiful wood, with tight growth rings and interesting grain patterns that reflect the forces the tree experienced during its lifetime. Trees in polar regions grow so slowly that a trunk the width of a pencil might be over 100 years old. In the harsh conditions near Earth's poles, where the growing season may last only a few weeks each year and temperatures rarely rise above freezing, trees have mastered the art of extreme patience. These polar trees represent some of the most remarkable examples of persistence in the natural world. Arctic willows and birches that grow in these extreme conditions often never reach more than a few feet in height, spending their entire lives as what appears to be low shrubs. Yet these seemingly small plants may be ancient, with root systems that have been growing for centuries. Some Arctic willows have been carbon dated to over 400 years old, despite having trunks no thicker than a human thumb. The growth rings in these polar trees are often so thin they can barely be seen without magnification. A tree might add less than a millimeter to its diameter over several years, creating wood so dense and fine-grained that it feels almost like stone. This incredibly slow growth creates some of the most durable and rot-resistant wood on Earth. These trees survive by growing close to the ground, taking advantage of the slightly warmer temperatures near the Earth's surface and seeking shelter from the constant polar winds. Their growth form, called krummholz or crooked wood, creates dense, matted structures that can withstand extreme conditions that would kill more conventional trees. During the brief polar summer, these trees must accomplish an entire year's worth of growth and reproduction in just a few weeks. They leaf out, photosynthesize, and produce seeds in a compressed growing season that might last only 6 to 8 weeks before winter returns. The extreme longevity of polar trees challenges our assumptions about plant life. These ancient organisms prove that life can persist in some of Earth's most challenging environments. Growing slowly but steadily through centuries of harsh conditions that would seem impossible to survive. Forest canopies create their own vertical climate zones, with temperatures and humidity varying dramatically from ground to treetop. Within a single forest, multiple climate zones exist, stacked vertically like floors in a building. The conditions at ground level can be dramatically different from those just 50 feet up in the canopy, creating diverse microenvironments that support entirely different communities of plants and animals. At ground level, forest conditions tend to be cool, humid, and relatively still. The thick canopy above filters out most direct sunlight, creating a dim, green-tinted world where temperatures remain fairly stable throughout the day. Humidity stays high because the canopy prevents much air circulation, and the soil continuously releases moisture through evaporation and plant transpiration. Midway up in the forest, conditions begin to change. More light penetrates through gaps in the canopy. Temperatures fluctuate more dramatically between day and night, and air movement increases. This middle zone often supports different plant species than the forest floor, including epiphytes that grow on tree branches and lianas that climb toward the light. In the upper canopy, conditions become almost desert-like compared to the forest floor. Temperatures can vary by 30 degrees or more between day and night. Humidity drops significantly as wind and direct sunlight increase evaporation. Plants growing at this level must be adapted to intense sunlight, temperature extremes, and periodic water stress. These vertical climate zones explain why tropical rainforests are so incredibly diverse. Each level provides different growing conditions, allowing forests to support far more species than would be possible in a single uniform environment. Many animals spend their entire lives in just one of these vertical zones, as specialized for their particular layer as fish are for specific depths in the ocean. The canopy also moderates climate conditions for the entire forest. By intercepting rainfall and releasing it gradually, by providing wind protection and temperature buffering, the upper branches create the stable conditions that allow the complex forest ecosystem to thrive beneath their protective shelter. Trees can live without sunlight for years by surviving off-stored energy reserves. Deep in the understory of dense forests, young trees often wait in near-complete darkness for decades, growing incredibly slowly while surviving on the merest scraps of filtered light. These patient saplings have developed the remarkable ability to enter a state of suspended animation, maintaining themselves on stored starches and sugars while they wait for their chance at the sun. When a gap opens in the canopy above, perhaps from a fallen giant or storm damage, these waiting trees can explode into rapid growth, racing toward the newly available light. They've been preparing for this moment their entire lives, maintaining their root systems and keeping their growth tips alive through years or even decades of near-starvation conditions. Some tree species can survive up to 7 years in complete darkness, slowly metabolizing their stored reserves while maintaining just enough cellular activity to stay alive. During this time, they may not grow at all, but they don't die either. They exist in a state of biological patience that few other organisms can match. This survival strategy explains why forest floors often seem empty of young trees, only to suddenly burst into life when disturbance creates openings. The seedlings were there all along, waiting invisibly in the shadows, ready to seize their moment when it finally arrives. The ability to survive prolonged darkness also helps trees recover from disasters. A tree that loses all its leaves to fire, disease, or defoliation can draw on these same energy reserves to produce new growth, tapping into decades of carefully stored resources to rebuild itself from nearly nothing. Certain trees can bend completely to the ground without breaking and spring back upright. In the windswept regions of the world, some trees have evolved an almost magical flexibility that allows them to bow down to the earth during severe storms and then return to their upright position when the danger passes. This incredible adaptation prevents them from breaking under extreme wind loads that would snap more rigid trees. The secret lies in their wood structure and growth pattern. These flexible trees, including many willows and some birches, produce wood with special fibers that can compress and stretch without breaking. Their cell walls are arranged in patterns that allow for extreme bending while maintaining structural integrity. Young trees of these species often look almost like living ropes, swaying and bending with every breeze. As they mature, they retain much of this flexibility while gradually strengthening their trunks. Even adult trees can bend at seemingly impossible angles, their tops sometimes touching the ground during severe storms while their roots remain firmly anchored. This flexibility serves multiple purposes beyond wind resistance. It allows trees to shed snow loads that might otherwise break their branches. It helps them survive ice storms that coat their branches in heavy, brittle shells. And it enables them to grow in locations where rigid trees simply cannot survive. The recovery process is equally remarkable. As soon as wind pressure decreases, these trees slowly straighten themselves, using the stored elastic energy in their bent wood fibers to return to their normal upright position. Within hours of a storm passing, what looked like a field of flattened trees can return to a normal forest appearance. Some trees communicate distress through color changes visible from space. When forests face large-scale threats like drought, disease, or insect outbreaks, they don't suffer silently. Many tree species change color dramatically when under severe stress, creating patterns visible from aircraft or even satellites orbiting high above the Earth. These color changes aren't random, but represent specific physiological responses to different types of stress. Trees facing water shortage often shift their foliage from deep green to yellowish or grayish tones as they reduce chlorophyll production to conserve resources. Trees under insect attack may turn reddish or brown as they increase production of defensive compounds. The scale of these color changes can be breathtaking. Entire mountainsides may shift from green to gold when beetle infestations spread through coniferous forests. Valley floors may turn pale and silvery when drought stress affects thousands of trees simultaneously. These aerial views reveal the forest as a single, interconnected organism responding collectively to environmental challenges. Satellite monitoring of forest color changes has become an important tool for forest managers and climate researchers. By tracking these color patterns over time, scientists can identify emerging threats, monitor the health of vast forest ecosystems, and even predict where fires or other disasters might be most likely to occur. The tree's ability to signal their distress on such a massive scale also demonstrates the synchronized nature of forest communities. Trees don't just change color individually, they often respond as groups, creating coordinated displays that reflect the shared challenges facing entire forest ecosystems. Tree rings can reveal the exact year a forest fire occurred centuries ago. Hidden within the annual growth rings of ancient trees lies a precise record of every fire that swept through their forest home. These fire scars appear as distinct marks in the wood, allowing researchers to create exact calendars of historical fire events going back hundreds or even thousands of years. When fire burns the base of a tree but doesn't kill it, the damage appears as a characteristic scar in that year's growth ring. As the tree heals over subsequent years, it grows new wood around the scar, but the mark remains permanently embedded in the tree's structure. By carefully examining these scars in multiple trees from the same area, scientists can determine not only when fires occurred, but how frequently, how intensely, and in which seasons. Some ancient trees carry the scars of dozens of fires throughout their lifetimes, creating detailed chronologies that reveal natural fire cycles stretching back through centuries. These records show that many forests experienced regular low-intensity fires every few decades, patterns that helped maintain forest health and prevented the buildup of dangerous fuel loads. The information locked in fire scars has revolutionized our understanding of natural fire cycles and helped forest managers develop better strategies for managing fire-prone landscapes. Trees that survived multiple fires provide living proof of which forest management techniques work best for long-term ecosystem health. By reading these ancient fire calendars, researchers have discovered that some of the largest and most destructive modern wildfires occur in forests that have been protected from fire for unusually long periods, allowing fuel to accumulate beyond historical norms. Trees can share water through their interconnected root systems during droughts. Beneath the forest floor, an underground economy of water sharing operates continuously, becoming especially crucial during times of drought when some trees have better access to water sources than others. Through their interconnected root systems and fungal partnerships, trees can literally share life-sustaining water with their neighbors. Trees growing near streams, springs, or other reliable water sources often act as community wells, drawing up moisture and sharing it through the underground network with trees in drier locations. This water sharing isn't just between trees of the same species, but can cross species boundaries, creating diverse mutual aid societies beneath the soil. The sharing mechanisms work through direct root connections and through the vast fungal networks that connect forest trees. Fungi can transport water across considerable distances, moving it from areas of abundance to areas of scarcity. In return, the fungi receive sugars and other nutrients from the trees they help. During severe droughts, this water-sharing system can mean the difference between forest survival and widespread tree death. Trees with deep roots that can reach groundwater continue supporting neighbors whose roots access only the dried upper soil layers. The forest community pools its resources, with some trees essentially sacrificing their own optimal water use to keep the entire community alive. Scientists have discovered that forests with intact underground networks show much better drought survival than forests where these networks have been disrupted. This has important implications for forest management and helps explain why maintaining forest diversity and soil health is so crucial for ecosystem resilience. Some trees can detect and respond to the footsteps of approaching animals. In the constant dance between trees and the creatures that might harm them, some species have developed the ability to sense approaching threats through ground vibrations. When large herbivores walk near certain trees, specialized cells in the roots can detect the subtle vibrations transmitted through the soil. These vibrations trigger rapid responses in the tree's defensive systems. Within minutes of detecting approaching footsteps, some trees begin producing bitter compounds in their leaves, making themselves less appetizing to browsing animals. Others may alter the chemical composition of their bark or increase the production of toxic compounds in their most vulnerable growing tips. The vibration detection system is remarkably sensitive. Trees can distinguish between the footsteps of different types of animals based on the frequency and pattern of ground vibrations. The heavy, regular steps of large ungulates like deer or elk create different vibration signatures than the lighter, more irregular movements of smaller animals. This early warning system gives trees precious time to mount chemical defenses before the actual browsing begins. Rather than waiting until they're being eaten to respond, they can prepare their defenses in advance, often deterring animals from feeding on them at all. The ability to sense approaching threats through ground vibrations also helps explain why some trees seem to suffer less browsing damage than others in the same area. Trees with more sensitive vibration detection systems can prepare more effective defenses, creating a kind of arms race between plant defensive capabilities and animal foraging strategies. Trees growing in urban environments often develop unique root patterns to navigate around underground obstacles. City trees face challenges unknown in natural forests, forced to grow their root systems around a maze of underground infrastructure, including water pipes, sewer lines, electrical cables, and building foundations. Over time, urban trees develop remarkably creative solutions to these obstacles, creating root patterns that would never be seen in natural settings. When a tree root encounters a buried pipe or foundation, it doesn't simply stop growing. Instead, the root system reroutes itself, growing over, under, or around the obstacle while continuing to search for water and nutrients. Some urban trees develop root systems that spiral around buried infrastructure, creating complex three-dimensional patterns as they navigate the underground cityscape. These adaptive root patterns often make urban trees more resilient than expected. By growing around obstacles, they create multiple pathways for water and nutrient transport, so damage to one part of the root system doesn't necessarily compromise the entire tree. Some city trees develop root networks that are more complex and interconnected than their forest counterparts. However, the constant navigation around obstacles also means urban trees often develop asymmetrical root systems that can affect their stability, A tree whose roots are forced to grow primarily in one direction by underground barriers may become more vulnerable to being uprooted during storms from certain directions. The patterns created by urban root systems tell the story of each tree's individual struggle to survive in the city. Like living maps of underground infrastructure, these root systems reveal the hidden landscape beneath our streets and sidewalks, showing how nature adapts to human-modified environments. Trees can continue photosynthesis at temperatures well below freezing in certain climates. While most of us associate photosynthesis with warm, sunny days, many tree species have adapted to continue this vital process, even when temperatures drop well below the freezing point. This ability allows them to extend their growing seasons and survive in climates where other plants cannot function. Evergreen conifers are particularly skilled at cold weather photosynthesis. Their needle-shaped leaves are designed to function efficiently at low temperatures, with specialized cellular antifreeze compounds that prevent ice crystal formation inside their tissues. Some species can continue photosynthesis at temperatures as low as -20 degrees Fahrenheit. The process requires special adaptations to prevent cellular damage from freezing trees that photosynthesize in freezing conditions, produce unique proteins that act as biological antifreeze, preventing ice crystals from forming inside their cells. They also adjust the composition of their cell membranes to remain flexible at low temperatures. Winter photosynthesis happens at a much slower rate than summer photosynthesis, but it provides valuable energy during months when deciduous trees are completely dormant. This extended growing season allows evergreen trees to accumulate resources gradually throughout the winter, giving them an advantage when spring arrives. On sunny winter days, these cold-adapted trees can actually produce significant amounts of energy through photosynthesis. The combination of bright winter sunlight reflecting off snow and the tree's ability to function at low temperatures creates surprisingly productive conditions for winter energy production. This adaptation helps explain why evergreen forests dominate in northern climates, where growing seasons are short. By continuing to photosynthesize throughout the winter, these trees can thrive in conditions where deciduous trees would struggle to accumulate enough energy during the brief summer months. Ancient stumps can live for decades by receiving nutrients from nearby trees through root connections. In old forests, the apparent death of a tree often isn't the end of its story. Ancient stumps, some centuries old, continue to live and even grow new tissue long after their trunks have been cut or fallen. Sustained entirely by nutrients shared through underground root connections with living trees nearby. These zombie stumps, as researchers sometimes call them, challenge our understanding of individual trees versus forest communities. The stump may have no leaves and no way to produce its own food, yet it maintains living tissue, slowly adding new growth rings year after year. Its survival depends entirely on the generosity of neighboring trees that share their photosynthetic products through the underground network. The phenomenon occurs most commonly in species that naturally form root grafts, where the roots of neighboring trees grow together and fuse. When one tree is removed, the connected root system continues to nourish the remaining stump, sometimes for decades. Some stumps have been found to be over 100 years old, sustained entirely by this underground life support system. These living stumps serve important functions in the forest ecosystem. Their root systems continue to stabilize soil and prevent erosion. They provide habitat for fungi, insects, and other organisms, and they may even contribute to the health of their supporting trees by helping to maintain the underground fungal networks that benefit the entire forest community. The discovery of long-lived stumps has changed how forest ecologists think about tree communities. Rather than viewing forests as collections of individual trees, these findings support the idea that forests function more like single, interconnected superorganisms, where the apparent boundaries between individuals may be less meaningful than previously thought. Trees can modify the soil chemistry around their roots to improve growing conditions for their offspring. In the ongoing competition for resources, parent trees don't just passively hope their seedlings will survive. Many species actively modify the soil chemistry in their immediate vicinity, creating more favorable growing conditions for their own offspring while potentially hindering the growth of competing species. This process, called allelopathy, involves trees releasing specific chemical compounds through their roots that alter the soil environment. Some of these chemicals make nutrients more available to the tree's own species, while making them less accessible to other plants. Others may inhibit the growth of competing seedlings, or even prevent the germination of seeds from different tree species. The chemical modification process is remarkably sophisticated. Trees can adjust their chemical output based on soil conditions, increasing the production of certain compounds when nutrients are scarce or when competition from other species is intense. They essentially create customized growing environments that favor their own genetic lineage. This soil modification continues throughout the tree's life and can persist for years after the tree dies. Some forest soils retain the chemical signatures of long-dead trees, creating patches where certain species grow better than others. These chemical footprints help explain why some forests develop distinct zones dominated by single species. The ability to modify soil chemistry also helps explain how trees can establish themselves in apparently hostile environments. By gradually changing the chemical composition of the soil around them, pioneer species can create conditions that eventually allow more diverse forest communities to develop. Parent trees often create chemical conditions that give their seedlings a competitive advantage during the crucial early years of growth. When young trees are most vulnerable to competition and environmental stress, this chemical nurturing represents another form of parental care in the forest community. Some trees can detect seasonal changes through root temperature sensors located deep underground. While we often think of trees responding to seasonal cues through their above-ground parts, many species also maintain sophisticated temperature monitoring systems in their root networks, sometimes extending several feet below the soil surface where temperature changes occur more gradually and predictably than in the air above. These underground temperature sensors allow trees to detect seasonal transitions with remarkable accuracy, often triggering seasonal responses weeks before air temperatures would suggest such changes are appropriate. A tree might begin preparing for spring growth while snow still covers the ground, responding to the subtle warming of deep soil layers that precedes surface warming by several weeks. The root-based sensing system provides trees with more reliable seasonal information than above-ground temperature monitoring alone. Air temperatures can fluctuate dramatically due to weather patterns, but soil temperatures at depth change slowly and steadily, providing a more stable indicator of true seasonal progression. Different tree species monitor soil temperatures at different depths, creating a range of seasonal response patterns within forest communities. Some trees respond to temperature changes in the upper soil layers, while others monitor temperatures several feet down. This variation helps prevent all trees in a forest from responding to seasonal changes simultaneously, spreading out resource demands and reducing competition. The underground temperature monitoring system also helps trees avoid false starts during unusual weather patterns. A tree relying only on air temperature might begin spring growth during an unseasonably warm winter period, only to have new growth damaged by returning cold weather. Trees monitoring deep soil temperatures are less likely to make such costly mistakes. This sophisticated seasonal sensing helps explain how trees time their growth cycles so precisely, beginning spring growth just as conditions become favorable and entering dormancy well before harsh winter conditions arrive. Trees can survive having up to 90% of their root system damaged and still recover completely. The resilience of trees to root damage is truly remarkable, reflecting millions of years of evolution in environments where roots face constant threats from drought, flood, disease, soil disturbance, and competition from other organisms. This extraordinary ability to recover from severe root loss helps explain how trees survive in harsh environments and recover from natural disasters. When a tree loses a large portion of its root system, it immediately begins an emergency response program. The remaining roots rapidly increase their growth rate, producing new root tips at an accelerated pace to replace lost absorption capacity. The tree also adjusts its above-ground growth, often shedding some leaves or slowing branch growth to match its reduced root capacity. The recovery process can take several years, but trees show remarkable plasticity in rebuilding their underground networks. New roots don't just replace what was lost. They often create more efficient networks, growing more directly toward water and nutrient sources. In many cases, the rebuilt root system becomes more effective than the original. This regenerative capacity varies among species, with some trees showing almost miraculous recovery abilities. Willows and poplars can regrow entire root systems from small fragments, while oaks and other hardwoods recover more slowly, but often more thoroughly. Even conifers, generally considered less resilient to root damage, can recover from surprisingly severe root loss. The ability to survive major root damage also explains how trees can be successfully transplanted, even as large specimens. Professional tree movers take advantage of this resilience, knowing that trees can survive the loss of most of their root system during the moving process and will gradually rebuild their underground networks in their new location. This root resilience has important implications for urban forestry and forest management, demonstrating that trees are often more capable of surviving soil disturbance and construction damage than commonly assumed. Forest trees synchronize their seed production across vast distances in a phenomenon called mast years. Every few years, Forests across entire continents seem to coordinate their reproductive efforts, with trees of the same species simultaneously producing enormous quantities of seeds over areas spanning thousands of square miles. These massed years create some of the most remarkable displays of synchronized behavior in the natural world. During a massed year, individual trees may produce 50 to 100 times more seeds than in typical years. The timing is so precise that trees separated by hundreds of miles often peak in their seed production within days or weeks of each other. Despite having no apparent means of communication across such vast distances, the synchronization appears to be triggered by specific weather patterns, particularly temperature and precipitation sequences that occur across large geographic regions. Trees seem to use these shared environmental cues as a natural coordination system, ensuring that when conditions are optimal for seed production and dispersal, all trees in a region respond simultaneously. This mass synchronization serves important survival functions. By producing overwhelming quantities of seeds all at once, trees can saturate the local population of seed-eating animals, ensuring that some seeds escape predation and survive to germinate. Animals simply cannot eat all the seeds produced during a massed year, no matter how abundant the animal population. The years between massed events also serve a purpose, essentially starving seed-eating animal populations and preventing them from building up to numbers that could consume all seeds produced. This boom and bust cycle keeps seed predator populations in check while maximizing the chances of successful tree reproduction. Massed years create cascading effects throughout forest ecosystems, influencing everything from soil nutrient cycles to wildlife population dynamics. The sudden abundance of seeds supports population explosions among many animal species, which in turn affects predator populations and even influences the spread of diseases carried by seed-eating animals. Trees can sense the length of nights and days with precision that rivals atomic clocks. Within their cells, trees maintain biological timepieces that track the changing length of days and nights throughout the year with extraordinary precision. This internal clock system, more accurate than many human-made timekeeping devices, allows trees to perfectly time their seasonal activities and coordinate their growth with the optimal periods for survival and reproduction. The light-sensing system operates through specialized proteins that can detect even minute changes in daylight duration. As days gradually lengthen or shorten by just a few minutes, trees register these changes and use them to trigger appropriate seasonal responses. Spring growth begins when day length reaches specific thresholds, while fall dormancy preparations start when nights reach certain durations. This precision timing prevents trees from making costly mistakes in their seasonal scheduling. A tree that began spring growth too early might lose new shoots to late frosts, while one that started too late might miss the optimal growing window. The internal clock system helps trees thread the needle between these competing risks. Different tree species are calibrated to respond to different day-length triggers, creating a staggered sequence of seasonal activities within forest communities. Some trees respond to the first subtle increases in day length, while others wait for more dramatic changes. This timing diversity helps reduce competition for resources and pollinators within forest ecosystems. The biological clock system also allows trees to prepare for seasonal changes well in advance. A tree might begin moving nutrients from leaves to roots weeks before actual leaf fall, guided by its internal calendar rather than waiting for environmental stress signals. This proactive approach to seasonal transitions gives trees significant survival advantages. The precision of tree timekeeping has fascinated researchers studying biological rhythms. Some trees can detect day-length changes as small as a few minutes, demonstrating timing accuracy that approaches the precision of atomic clocks. While operating entirely through biological processes, mature trees create nursery environments that increase seedling survival rates by up to 300%. In the forest community, adult trees don't just compete with younger generations for resources. Instead, they often create specialized environments that dramatically improve the survival chances of seedlings, including both their own offspring and the young of other species. This nursery effect transforms the area beneath mature trees into protected growing zones where the next generation of forest can establish itself. The nursery environment works through multiple mechanisms. The canopy of mature trees filters harsh sunlight, creating the dappled shade conditions that many forest seedlings require during their vulnerable early years. The leaf litter from adult trees creates a rich organic layer that retains moisture and slowly releases nutrients, providing ideal growing medium for young plants. Mature trees also modify the soil chemistry and structure around them through their root systems and associated fungi. These changes often create conditions that are more favorable for seedling establishment than the surrounding forest floor. The soil beneath old trees typically has better structure, more organic matter, and more diverse microbial communities. The protective effect extends beyond physical conditions. Mature trees often harbor populations of beneficial insects and other organisms that help protect seedlings from pests and diseases. The complex ecosystem that develops around old trees includes many species that provide indirect benefits to establishing young plants. Research has shown that seedlings growing within the influence of mature trees have dramatically higher survival rates than those attempting to establish in open areas or beneath younger trees. This nursery effect helps explain why forest regeneration is often most successful in areas with some remaining mature trees rather than in completely cleared areas. The creation of nursery environments represents another form of intergenerational care in forest communities, where the older generation actively improves conditions for the younger generation, ensuring the continuity of the forest ecosystem across centuries. The heartwood of some trees can remain intact for thousands of years after the tree dies. When a tree reaches the end of its life, not everything perishes at once. The heartwood, the dense central core that provided structural support throughout the tree's lifetime, can persist long after the outer layers have decayed away. This remarkable preservation creates some of nature's most enduring monuments, wooden time capsules that can last for millennia. In certain climates and conditions, fallen trees become naturally mummified. The heartwood's density and chemical composition make it resistant to the bacteria and fungi that typically break down organic matter. Some species produce heartwood so durable that ancient logs can be found perfectly preserved in bogs, deserts, and other protective environments. Their wood still solid and workable after thousands of years underground. These preserved remnants tell stories of ancient forests, climate changes, and geological events. Scientists can examine wood from trees that died thousands of years ago, learning about past environments and atmospheric conditions. The wood remains so intact that it can still be used for construction or crafting, creating objects made from trees that lived and died long before human civilization began. In coastal areas, ancient trees swept into rivers during prehistoric floods sometimes become buried in sediment, where the lack of oxygen prevents decay centuries later. These ghost trees emerge during storms or erosion events, their wood as sound as the day they fell. These discoveries provide glimpses into vanished forests and remind us of the incredible durability hidden within living trees. Tree bark contains natural compounds that have been used as medicine for over 5,000 years. Long before synthetic pharmaceuticals, humans discovered that tree bark held powerful healing properties. The inner bark of various tree species contains complex chemical compounds that can reduce pain, fight infection, and treat numerous ailments. These natural pharmacies growing in forests around the world have provided medicine for countless generations. Willow bark contains compounds similar to aspirin and has been used to relieve pain and reduce fever for millennia. Indigenous peoples across different continents independently discovered this remedy, chewing willow bark or brewing it into teas for treating headaches, arthritis, and other inflammatory conditions. The active compounds in willow bark work gently and sustainably, providing relief without many of the side effects associated with synthetic alternatives. Other tree barks offer different medicinal properties. Cherry bark soothes coughs and respiratory ailments. Birch bark contains compounds that support skin health and wound healing. Pine bark provides antioxidants that support circulation and overall wellness. Each species has developed its own unique chemical arsenal, refined over millions of years of evolution. The sustainable harvest of medicinal bark has been practiced by traditional cultures for generations, taking only small amounts from living trees without causing permanent damage. Modern research continues to discover new therapeutic compounds in tree bark, leading to the development of medicines that save millions of lives while honoring the ancient wisdom of forest-based healing. Some trees can live underwater for months during seasonal floods. In floodplains around the world, certain tree species have mastered the art of underwater survival. When rivers overflow their banks and forests become temporarily submerged, these aquatic adapted trees don't just endure the flooding. They continue their essential life processes even while completely underwater. The secret lies in specialized adaptations that allow trees to function without direct access to atmospheric oxygen. Some species can switch their cellular processes to operate in low oxygen conditions, much like deep-sea creatures. Others have developed internal air storage systems that provide oxygen reserves during submersion periods. Underwater trees often enter a state of reduced activity, slowing their metabolism to conserve energy and oxygen while maintaining essential functions. Their root systems may actually benefit from the periodic flooding, receiving nutrients and minerals carried by the floodwaters. When the waters recede, these trees often show vigorous growth spurts. Having been nourished by their aquatic experience, mangrove trees represent the ultimate example of this adaptation, spending their entire lives with their roots in salt water. But even temperate forest trees in flood-prone areas have developed remarkable tolerance for temporary submersion. These adaptations allow forests to thrive in river valleys and wetlands where seasonal flooding is a regular occurrence. The ability to survive underwater flooding also helps trees recover from extreme weather events. Forests that might otherwise be destroyed by major floods can bounce back quickly if the trees have adaptations for underwater survival, maintaining ecosystem continuity through natural disasters. Trees produce natural antifreeze compounds that prevent cellular damage in extreme cold. When winter temperatures plunge far below freezing, trees don't simply endure the cold. They actively resist it through sophisticated biochemical defenses. These natural antifreeze systems allow trees to survive in climates where unprotected plant tissue would be destroyed by ice crystal formation. Tree antifreeze works differently from the ethylene glycol used in car radiators. Instead of simply lowering the freezing point of water, biological antifreeze compounds prevent ice crystals from growing large enough to rupture cell walls. These specialized proteins and sugars bind to tiny ice crystals, keeping them small and harmless while allowing cellular processes to continue even at temperatures well below the normal freezing point of water. Different tree species produce different types and concentrations of antifreeze compounds, allowing them to survive in their particular climate zones. Arctic trees may have antifreeze systems that function at -40 degrees, while temperate species might only need protection to -10 degrees. Each species has calibrated its chemical defenses to match its environmental challenges. The production of antifreeze compounds requires energy, so trees carefully regulate when and how much they produce. As autumn progresses and temperatures begin dropping, trees gradually increase their antifreeze production, reaching peak concentrations by the depths of winter. In spring, as the threat of hard freezes diminishes, trees reduce antifreeze production to conserve energy for new growth. Some trees can detect and respond to specific insect pheromones in the air. In the ongoing evolutionary arms race between trees and the insects that feed on them, some tree species have developed the ability to eavesdrop on insect chemical communications. By detecting the pheromones that insects use to coordinate their activities, trees can prepare defenses before attacks even begin. When bark beetles release pheromones to signal a mass attack on a tree, nearby trees of the same species can detect these chemical messages and begin producing defensive compounds immediately. This early warning system allows trees to mount chemical defenses while the attacking insects are still focusing on their initial target, potentially deterring them from spreading their assault to additional trees. The chemical detection system is remarkably sensitive, capable of identifying specific insect species based on their unique pheromone signatures. Trees can distinguish between the chemical signals of different types of threats and tailor their defensive responses accordingly. The compounds produced to deter leaf-eating caterpillars are different from those used against bark-boring beetles This chemical eavesdropping also allows trees to coordinate their defenses across forest communities. When one tree detects insect pheromones and begins producing defensive compounds, it often releases its own chemical signals that warn neighboring trees of the approaching threat. This creates cascading defense networks that can protect entire forest stands from insect outbreaks. The ability to intercept and interpret insect communications represents one of the most sophisticated examples of plant-animal chemical warfare, demonstrating the complex chemical conversations that constantly occur in forest ecosystems, most of them completely invisible to human senses. Tree leaves can orient themselves to track the sun's movement across the sky throughout the day. While we often think of plants as stationary, many tree species actually exhibit subtle but continuous movement as their leaves adjust position to optimize light capture. This solar tracking behavior, called heliotropism, allows trees to maximize their photosynthetic efficiency by keeping their leaves properly oriented toward the sun as it moves from east to west. The movement happens gradually and quietly, often imperceptible to casual observation, but measurable over the course of hours. Specialized cells at the base of leaf stems can expand or contract in response to light direction, creating the mechanical force needed to adjust leaf position. Some leaves can rotate as much as 90 degrees during a single day, always maintaining optimal angles for light absorption. And now, as our gentle journey through the forest of facts comes to its quiet close, let your mind settle like evening mist among the branches we've wandered together through the hidden wisdom of these ancient beings, discovering their secret conversations, their patient endurance, and their quiet acts of care that span centuries. From the bristlecone pines that have weathered millennia to the underground networks that connect entire forests in silent communion, trees have shown us that life's greatest mysteries often unfold in whispers rather than shouts. May you carry their lessons of patience, resilience, and gentle persistence into your dreams tonight. Sleep well, knowing that somewhere trees are growing, breathing, and keeping their ancient watch over our world.